Good morning, 11th grade. Hope you guys are doing well. It is Monday, first Monday of May, and you know what that means? 3 weeks. That's all you guys got left. 3 weeks of school, and then you will be done for the semester, done with your junior year, and then you'll officially be seniors. Isn't that awesome to think about? Probably kind of scary at the same time too. I remember that feeling. But I hope you guys had a great weekend and that you enjoyed your time in church or whatever it is you did this weekend. We are going to pick up with the third section of notes for chapter 17, just so you guys are kind of aware of where we're going as far as chemistry goes. We are going to do section 3 notes video this week. We're going to do section 4 notes video next week. Next week in your work folders, you'll be getting the study sheet for the final exam that you will need to fill out. When you come back that Monday, I'm going to be checking those study sheets to make sure that you guys have the right information, that you've been studying what you need to be studying. That way you can be prepared for the final exam that week. I don't know what day your exam is going to be yet. Nobody's told me. I believe they're still working that schedule out. But just so you guys are kind of aware where we're going with chem, this is the tentative plan, all right? We're going to finish the chapter between this week and next week. Next week you're going to get your study sheet. That way you can have it to be studying for the exam the following week. So, here we go. Let me have a drink first. Alright, nuclear reactions. Now, nuclear reactions may be described by nuclear equations that show the atoms or particles that react and the products they form. So basically, a nuclear reaction can be broken down into a math equation. That's really all this is saying. Now, it's not a specific math equation, like a formula that you would follow, but they can be broken down, okay? Rules for nuclear reaction equations. If you were to write one, this is what you would need to do. Again, we're not going to be doing any of the math just because I don't want you guys to try to learn that over video. There's no need to put extra stress on you at this point. So, just some brief rules to at least familiarize yourself with. All right, that way if somebody says it, you can say, hey, I kind of remember that happening in chemistry a little bit. Okay, the mass number must be conserved, meaning the sum of the mass numbers of the reactants must equal the sum of the mass numbers of the products. Okay, think back to the law of conservation of matter and energy. Matter can neither be created nor destroyed, but it can change forms. So with that in mind, in a nuclear reaction, the amount of the reactant has to equal out to the amount of the product. Now the reactants might change a lot of forms to get to this product, but they still have to equal out. Okay, if you start with 5, you got to end with 5. Okay, you don't start with 5 and end up with 10. Okay, it's conserved, it stays the same. And then the nuclear charge or the atomic number must be conserved, meaning that the sum of the atomic numbers of the reactants must equal the sum of the atomic numbers of the products. Okay, let's say, just for argument's sake, the atomic number you're working with is 238. Okay, which does happen. If you watch the chemistry quiz assignment video that you're supposed to watch this week, you'll see that number. Anyway, if it is overall 238, then the reactants must add up to get 238. So types of nuclear decay, that's what we're going to focus on mainly with this section is nuclear decay, all right? And there are 3 main types of nuclear decay, all right, alpha, beta, and gamma. So, all radioactive decay is the converting of one nuclide into another, okay? Anytime something breaks down, it's really just changing form, it's converting, all right? So, alpha decay, this occurs when an unstable atom ejects a clump of 2 protons and 2 neutrons. This 2 proton, 2 neutron combo is called an alpha particle, okay? So if it emits the alpha particle, 2 protons, 2 neutrons, It's done in order to reach a stable state. Now, any type, if you remember, I think last week, maybe the week before, I can't remember what video I talked about it in at this point. But radioactive decay, all radioactive decay occurs for an element or a group of elements to reach stability, okay? Remember, atoms want the path of least resistance, okay? They want to do the least amount of work possible. So they are going to seek the least active state in order to do that, okay? They are going to seek to reach stability. So one way they do that is by alpha decay. They emit those 2 protons, those 2 neutrons, that alpha particle, in order for stability to be gained. Okay, the atom will have an atomic number 2 less than it originally had, making it a different element, okay? Now, it can change into new elements, okay? Decay allows new elements to be created, but the overall mass, the overall amount of substance that you started with does not just poof into thin air, all right? You still have to have, even if it goes down to another element, there's 2 protons and those 2 neutrons, they got to do something, okay? Now, alpha particles are actually positive ions of helium-4. So the alpha particle that's emitted actually is a helium-4 ion, okay? So again, it doesn't just disappear into thin air, it becomes something else. And then if you put them back together, you put the helium-4 back together with the substance that it had decayed into, you would have the original overall mass number, the original amount of energy there, everything would be conserved. All right, alpha particles are attracted to the negatively charged plate in an electric field. So because it's 2 protons and 2 neutrons, those are equal. So the positive is balanced out there, but because it's a positive, there's no negative in a proton and a neutron combo. So it's going to seek to that negative because opposites attract. This is the most common type of decay in elements with atomic numbers greater than 83. The atomic number Z, remember all the way back to the very beginning of chemistry, atomic number is designated with the letter Z, decreases by 2, and the mass number, A, again, remember all the way back to the beginning of chemistry, that's what mass number is designated with, is the capital A, decreases by 4 with alpha decay. Beta decay. All right, beta decay. This occurs when a neutron in an atom's nucleus changes into a proton and emits an electron, a beta particle, in the process. So, let's say an atom is how do I want to say this? Sorry guys, I thought I knew where I wanted to go with this, and then I don't know, but I'm here. It's life. Plus it's Monday, and I haven't had all my coffee yet. I'm struggling a little bit. I'm just gonna be honest with you. So, anyway, so a neutron changes into a proton, okay, and it kicks out an electron during the process because it is seeking that stability, okay, and if there are extra electrons hanging out, when that proton is converted, it kicks out the electron, allowing the substance, whatever you're working with, to reach stability. Anyway, that electron that is kicked out is known as a beta particle. All right, they are negatively charged and are attracted to the positively charged plate in an electric field. Okay, remember opposites attract. So you kick out an electron which is negatively charged, it's going to seek to the positive. Beta decay results in an atom with an atomic number 1 higher than that of the original atom while leaving the mass number unchanged, okay? So beta decay, with beta decay, we're working with cations or anions, okay? The overall substance itself hasn't changed, okay? Let's say we're still working with oxygen, okay? But we're working with the cation or the anion of oxygen. which means that atomic numbers are different. Beta decay consists of high velocity electrons, and then with beta decay, the atomic number increases by 1, and there's no change in the overall mass number, because remember, you're still working with the same substance. It's just, if you've gained 1, then you are technically dealing with a cation, okay? Then you have gamma. This releases gamma radiation, which is electromagnetic waves of very high frequency and energy. Gamma radiation is the one that you hear about, and everybody freaks out and they're like, oh no, we're gonna die. Well, that's because it's really dangerous, okay? This occurs in nuclei that have just undergone alpha or beta decay, so one of the previous decays have to have occurred in order to set the stage for gamma decay to happen, okay? Either alpha decay or beta decay must have happened in order for gamma to come in onto the scene. Gamma rays are uncharged, they are not deflected by fields, and they easily penetrate solid substances, okay? Now, actually we're going to talk about it on another slide, so I'm not going to go through that yet. Gamma decay does not change the atomic number or mass number of the element. And then you have neutron radiation. Neutron radiation is interesting because you don't hear it talked about a whole lot, okay? Neutron radiation is kind of like the ugly stepchild of radiation. It's one of those things like we know it's there, but we never talk about it, okay? So neutron radiation, this is caused by neutrons being ejected from the nucleus, okay? It does happen. Neutrons can be kicked out by themselves. So because neutrons are unchanged, now, when they are kicked out, they're not changed, okay? That's something to keep in mind. So because they are unchanged, they can easily pass through many types of matter with little to no interaction, okay? Neutrons can pass through just about anything and it not cause any interaction. Nobody ever knows it's there, okay? Nobody ever knows it happened. They are only deflected or absorbed if they collide directly with an atomic nucleus. So if they happen to hit the nucleus directly, then they can be absorbed, or if the nucleus chooses, because it's already at a stable state or something like that, then it will deflect it, reject it, and send it away. Neutron radiation is used to produce transuranium elements by bombardment reactions, and we're going to talk about bombardment reactions later on, but basically it's when you overwhelm the nucleus with an excess of neutrons or protons or electrons, okay? And transuranium elements are elements with atomic numbers beyond that of uranium element 92. Transuranium elements are going to be important later on, hence why we define them here. Okay, the penetrating ability of radiation. This is why I didn't talk about it when we talked about gamma rays. Okay, most alpha radiation cannot penetrate paper. Okay, alpha particles, they are not very strong. They can't get through much. Okay, honestly, you could hold up a sheet of paper in front of an alpha particle reactor, have one shot at the piece of paper, and it would probably bounce off. It probably wouldn't go through it at all. Beta radiation has more penetrating ability than alpha. Beta penetration can get through paper, it can get through plastics. Typically it's stopped by like woods and steels. And then gamma radiation is extremely strong and can penetrate almost all substances. There are very few things, unless they are scientifically engineered, that can originally just in their natural state stop gamma radiation. And then penetrating abilities in decreasing order is gamma, beta, alpha, gamma being the highest, beta being in the middle, and alpha being the least. All right, half-lives. All right, half-lives. These are the length of time it takes for 1/2 of the original substance to decay into a new substance. All right, so let's say, well, let me back up, okay? Every element on the periodic table has a length of time, be it days, weeks, or years, okay, depending on the element. Every element has a certain length of time in which it will decay into a new substance, okay? So the half-life, or I'm sorry, in which it will decay completely. Let me back up there. A has a length of time in which it will decay completely, be gone. Can't find it anymore, okay? If it's just chilling out in its natural state, right? So, with that in mind, there are half-lives, and that's the amount of time that it takes for that original substance to decay into a new substance, okay? And it is done in halves, okay? So, let's say it takes an element 100 days to completely decay, and it is no more, okay? It is completely absorbed into something new. So, takes 100 days for that to happen. The half-life of that element would be 50 days, okay? It now takes 50 days for that element to break down into a brand new element, okay? The substance that is changed during the half-life decay changes into the daughter nuclide, okay? So that 50-day, substance that's created on day 50, that is considered the daughter element of the parent element that was at 100 days, all right? Now, the amount of nuclide remaining after each half-life is 1/2 of what you started with, okay? So you started at 100, you go down to 50, it drops to 25, 25 would drop to 12.5, yeah, 12.5, and then that breaks down further into 6.4, and then that breaks down, okay? Not 6.4, what would that, 6.3? 6.2 and 0.5? 6.25. Yeah, 6.25. Sorry, guys. Okay, activity. The half-life of a substance determines the intensity of the radiation it produces, okay? The weaker, the larger the half-life, okay, if you're dealing with half-lives in years, okay, then it's not going to be as strong versus as if you're dealing with something in days, because it's a rapidly decaying if it's working in days, right? If you're working in years, it's taking a long time for that to break down. Oh, excuse me. It's taking a long time for that to break down, get to where it wants to be if you're working with years. So something that decays in days or weeks is much more dangerous than something that decays in years. So activity is the amount of decay occurring in a radioactive substance. The SI unit for activity is the becquerel, okay, BQ. You can read that in your textbook if you want to know why it is that way. I'm not going to take the time to go through all of it. Substances that decay rapidly produce intense radiation that lasts for a short time, or high activity. Substances that decay slowly produce low levels of radiation that can last for years, or low activity, okay? Low activity is much less dangerous than high activity. The radioactive decay series. This is a long series, a chain basically, of radioactive nuclides, I don't know why I keep saying it that way, ending in a non-radioactive stable nuclide, okay, so stable substance. It breaks down to stability. That's all that a radioactive decay series shows you. It shows it going from where it's radioactive and dangerous, breaking down into that stable form. Okay, unstable atoms will decay until they reach a stable nuclide. That's nothing new. We've talked about that. Okay, they're going to seek the path of least resistance. They're going to want that stability. All naturally occurring radioactive heavy elements with atomic numbers greater than 83 belong to one of three series: the thorium series, the uranium series, or the actinium series. All of these involve either alpha or beta emissions, and each one is used in some form of nuclear power. The bombardment reaction, okay? This is when nuclear reactions are induced by pelting a sample with other particles, okay? So those particles, again, it can be not where I'm going with that. Electrons, protons, or neutrons, depending on what type of reaction you are trying to create. But you're basically hitting the atom with a bunch of extra particles that it doesn't originally have in order to create an unstable state in order to allow a nuclear reaction to take place, okay? So neutrons are typically used to induce these reactions. However, alpha particles, protons, duoneutrons, and ions of various other elements may be used as well. Particle accelerators use magnetic and electric fields to accelerate charged particles to energies of several million electron volts to initiate nuclear reactions. The bombardment reactions are used to prepare the trans-uranium elements, okay? So trans-uranium elements are those elements with atomic numbers higher than, what did I say it was, 93? 83? I can't remember. It was a couple slides ago at this point. Anyway, sorry guys, it's Monday. I'm gonna cover it up with that blanket statement of it's Monday. Anyway, there we go. And that's where we're gonna stop for the day, because we're gonna do this series of slides next week and just round out the school year with chapter 17. There is one whole other chapter that we won't get to cover just because of time. You are welcome to read chapter 18 on your own if you are so compelled and you just want to know, what am I missing for that last chapter of chemistry? Then you can read chapter 18 on your own, but I'm not going to make you. So I hope you guys have a great week. I hope that you are getting all of your work done for all of your classes and that you're staying on top of things. Don't slack off now. You're almost done. Stay on top of it. I miss you guys. I'm praying for you.